Example 5. A projectile on Earth will be launched eastward at a velocity v meters per second and with a launch angle theta north of east. The horizontal range of the projectile is given by this function. So here they give us the function. What is the maximum range attained, and what optimum launch angle produces this maximum range? Okay. So, really, we have our function. We really just need to define our function on an interval. Well, if we wanted to travel eastward, we could do an angle from 0 to pi over 2. Okay. So we want to find critical points. So r prime of theta. This is 2v squared over g. We've got a product rule here. So cosine squared theta minus sine squared theta if we do our product rule and simplify. That's what we get. This is a continuous function, so the derivative exists everywhere. So we only have to worry about when the derivative, r prime of theta, equals 0. And this happens precisely when this expression here equals 0. Now, there's a couple ways you could go about solving this. A couple ways you could go about it. One way is to know that this is the double angle identity for cosine. And the only time that cosine of an angle equals 0 is when that something, that angle, is pi over 2 plus any integer multiple of pi. Right? Because a cosine, it's 0 at the top, that's pi over 2, or you can add, rotate by pi, end up down here, that's 3 pi over 2. Or you can write this as pi over 2 plus pi. Or all the way back up again here, which would be 5 pi over 2. And then you can keep going all day. But because our domain here is only 0 to, well, actually, let's solve this first. Let's solve this for theta. So this would be pi over 4 plus a whole number multiple of pi over 2. So I'm just going to say where k is an integer. So this symbol here, we know that this means all real numbers. Well, this symbol here means all whole numbers, positive, negative, or 0 whole numbers. So this is for any integer k. So here, this can be any add or subtract any multiple of pi over 2. So if you think about it on our unit circle here, when k is 0, that's right here at pi over 4. But if we add, so if k is equal to 1, we add pi over 2, that would put us over here at 3 pi over 4. When k is 2, that would put us over here at 5 pi over 4. And even if we go backwards, right, if we do negative 1 for k, then we'd subtract, we'd rotate clockwise by 90 degrees, which would end up here at, we could write this point as negative pi over 4, or it's equivalent on the unit circle to being 7 pi over 4. These values numerically are not equal, but as far as what they represent as to the extent at which they represent a location on the unit circle, they represent the same location, so we would say that they are equivalent. Not equal, but they are equivalent. So notice here that none of these live in our domain of the first quadrant. So this means pi over 4 has to be our answer. So I'll say only pi over 4 is in our interval from 0 to pi over 2. So theta equals pi over 4 is our critical point. Now we want to compare values. So what's the range when we have an angle of 0, a range of an angle of pi over 2, and a range of an angle of pi over 4? So if we plug them into our function right here, we'll see that when theta is 0, sine is 0, so this whole thing is 0. And when cosine is pi over 2, that makes cosine 0, so this whole thing is 0. So these first two options, we get 0. And then if we plug in pi over 4, we end up getting v squared over g. And this is our maximum range. So a maximum. So the maximum range is v squared over g, and results from a launch inclination angle of pi over 4.